think I know everybody here, just about. And so I want to talk a minute about the grid, because there's all these terms that get thrown around, and it's like, it's hard to form a picture of what a grid, electrical grid is. But as I was thinking about it today, it's really probably the greatest human achievement on the planet. It certainly has more money invested in it than any other infrastructure on the planet. The electric power industry is the most capitally intensive business in the world. So worldwide, I forget how many $1 trillion are invested in electric infrastructure, but you could say, well, what about a spaceship? Well, you think about the launch pad and all of the grid connected part of the whole space program. The whole space program is just part of the electrical grid. And that rocket ship, that put man on the moon, the quality and accuracy of the sensors and the equipment and the computers on that rocket ship is much less than what we have just in one of our power plants right now. We have all that horsepower and sensing and interactive control system. So that's just one little tiny power plant, one little tiny community. And yet the US grid connects all these hundreds and thousands and millions of industries. And somehow it just all works. The lights stay on. And you say, well, Jeremiah, because a lot of people, they say, that was one of the big questions to scientists. What was the biggest innovation in the 20th century? And they said mass communications. That was the biggest innovation in the last century. Biomedicine is going to be the biggest human gains in this century. But I would argue that whole communications network is also just part of the grid. It's just one element of how the grid all talks to each other, shares information, and it's almost like a little bit of magic. So I've learned a lot over the last 2 years in working with these projects, and what I've kind of learned is the technology is nowhere near where I thought it was. You think of a solar farm or a wind turbine is something that you can just plug into a grid and works, and it doesn't. It's extremely complex, and it's hard to get these things to handshake together in an economical way, and even many times in an operational way. And by in a way, there's some aspects of the grid that have kind of gotten away from us, and there's good aspects to that and bad aspects of it. But I guess I'll kind of dive into what the RADIANCE project itself is, and this is a mouthful. Resilient Alaskan distribution system improvements using automation, network analysis, control, and energy storage. And basically that boils down to taking our electric system, using some technology and some software and modeling tools from the national laboratories, and making some little tweaks to our grid. We want it to be capable of doing more things. And the things that we can do with our grid, they want to try here in Cordova so they can apply them to the national grid. So, and it turns out, I think if you can come up with a real sexy acronym like RADIANCE, you have a better chance of getting funded. But so the Department of Energy realized that the grid was so complicated and there's so many different parts of it, and in many places there's different regulatory agencies. You might have one company owns a power plant, another company owns a transmission line, a different company owns a local utility. So you might have 4 or 5 different owners just in one electric delivery system, and each of those has its own federal and state agencies that regulate what they do. So for a generator clear up here to talk to somebody's home refrigerator in a smart way and kind of collaborate to use energy more wisely, it's very difficult. You got all these company barriers and communications barriers and regulatory barriers. So one of the great things about Cordova is we're kind of a playground. You as the members own everything right up to the generators. So if you want your refrigerator to reach out and run when there's excess hydroelectric available instead of spilling, or charge your electric vehicle, you can just tell your board of directors, let's move this direction. And we've kind of backed into we're moving this direction because it's a cost-effective and efficient and a more reliable way to move. It's just a lot more complicated than we thought at first. So the Department of Energy realized this is way too complicated for any one lab, any one vendor, any one utility to figure out. So they started creating what they call this Grid Modernization Laboratory Consortiums. Everything's a mouthful with the Department of Energy and the national labs. But basically it says, we want several of you working together. We want, when you bring a project to us, we want to see several laboratories, we want to see some universities, we want to see private equipment companies, we want to see local electric utilities. We want to see you all working together to solve these problems, because you're going to have to. Nobody can figure this out themselves. So we were fortunate to be able to host a Senate Energy field hearing here in Cordova a couple of years ago. And Senator Murkowski brought a leader from Sandia National Laboratory, Abraham Ellis, and we have two great project leaders on our Radiance project. One is Abraham Ellis, and the other is Rob Hovsapien. And Abraham grew up in a small town that was off-grid in Panama, so he's kind of lived this experience, and now he's one of the leaders at the National Lab. And when he came here for the field hearing, and we were kind of showing him our system, and other Alaskans were explaining how we do business and how we make things work, a lot of time in remote places and with limited resources, he's like, what are we thinking? Here we are in national labs spending all these time and resources and money trying to develop microgrid technologies and stuff, and you guys have been doing it, in Cordova's case, for over 110 years. Because Humpback Creek was built in 1907, so ironically we've gone from 100% hydro to 100% diesel, and now we're going back. But Abraham says, we should be working with you. We you guys have street smarts and understand how to actually make this stuff work in ways that even we don't. So 3 or 4 months later, he called and said, hey, there's this new round of grid modernization grants available from Department of Energy. Are you interested? And we said, well, we're moving in that direction. We want our grid to be smarter. We want our customers to have choices in whether they want to generate their own power, or whether they want solar, or as tidal power and other things develop. We just want the members here to have choices, and we want to be able to provide reliable power and do it affordably, have it be feasible. So if we can work together and move in that direction, then yes, we'd like to partner with you. So it turns out that after 20 years of making a lot of investments in technology and hydro plants, we kind of are at a point where we have to do a lot of upgrades anyway. Our copper communication lines corrode. We're replacing them with fiber, with Cordova telephone cell. As our old computers, your computer might only last 5 years at home. Our industrial computers, called programmable logic controllers, last 15 to 20 years. So, well, you should replace them after 10 maybe, but we're at a point where those need to be replaced, and the new ones have great features that can help us run more efficiently. So we had to make a lot of upgrades anyway, and it turned out about $1.5 million worth over 3 years. And then the National Laboratories said, well, we'll bring $6.2 million to that and work together to do some of these technologies. So I'll just kind of walk you through, and there's going to be some really busy screens here, and I'll try to boil it down a little bit, but it is kind of technically complicated stuff. So,
you want the lights down?
Yeah, that would help actually. And I'll try to use the pointer here. So this is the big, huge project team, and we've got Idaho National Lab, Sandia National Lab, and Pacific Northwest National Lab are the primary laboratories. And then we have the National Rural Electric Cooperative Association actually represents 1,000 electric cooperatives across the country and a few internationally. And they have their own technology strategy group that is really world class. I mean, they compete with the national labs, but they understand little utilities and limited resources. They understand what cybersecurity looks like for a company that only has 15 or 16 employees, and strike that balance between being secure and being able to afford it. So we brought them in as a partner, and they've been great. In fact, they funded a full intern for us for the whole summer last year. They really helped us with data collection and organization. And then our own Alaska Center for Energy and Power, and the director Gwen Holdman, and that kind of developed the Chena Hot Springs, where they were making electricity from hot water. And she's the director of that program at the University of Alaska Fairbanks. And she also provided an intern for the whole summer. Alaskan engineering students that went outside for school came back and worked here for the summer to help us out and hopefully get interested in the electric utility industry, and or maybe even moving to a place like Cordova. And then Alaska Village Electric Cooperative with Mira Kohler is the manager there. And they're also working as a utility partner. And then we have several universities. And we broke it up so that everybody has a distinct role. Now Cordova Electric is going to be involved with the whole project the whole time, because we're building it on our electric system basically. And then these other universities, they might do one piece of modeling, they might just work on the cybersecurity piece, they might just work on another piece. And then we meet weekly by teleconference, and then we've broken it down into 3 what we call integrated project teams. And I'll explain that here in a sec. So the idea behind a resiliency framework is that kind of as an outshoot of hurricanes Rita and Katrina and some devastating storms on the East Coast, especially Rita, they noticed, hey, you know, most of us got blacked out, but there's these little towns that might have had an old diesel generator or hydro nearby. They were able to get their lights back on in a few hours, whereas some of these cities had to wait for, you know, days and days and days. Isn't there a way to make systems more resilient in the face of a disaster? And so there's 100 definitions of resiliency, but the one that's kind of sticking is a resilient system is one that can anticipate a problem, that can withstand that problem better, and it can more quickly recover from a problem. So for us, we've already built a lot of resiliency into our system, and underground power lines is a great example. You don't really have to anticipate a storm because it's so hardened. We withstand windstorms so well that we really don't have to do anything special. Say a windstorm's coming, we don't put any extra staff on, we aren't ready to be, you know, prepared for call-outs. When I first got here, we would have trucks warmed up, have fuses laid out, we'd have everything ready for game time because we'd know there were gonna be trees through lines. We don't even blink now, so, and mostly the lights don't. So I'm gonna pause because it's not being very interactive with me rattling on at 1,000 miles a minute. But is there any questions or so far?
What about earthquakes? I know you got your underground lines, but how resilient are they?
That's a great question. So, and that's a good kind of segue into what a resilience metric is. So, and Heather is here with us from our own Cordova Emergency Management. They've been participating in this process as well because this is really about system security. But so we developed metrics, and those metrics were like earthquake, tsunami, volcano. Because ironically, when a big volcanic ash plume goes up, we don't want to be running our diesels. It's that glass is very abrasive. It can cause a lot of damage. So we have a lot of extra filter sets on hand. Some of our diesels pull the air in through an oil bath that can help. But if that happens in the middle of winter, we don't have a lot of hydro. We really don't want to run our diesels, so that's a bad scenario for us. So a tsunami. It can, you know, big enough tsunami might hit our lowland areas that has our Humpback Creek project, our diesel project, but Power Creek would be okay. And so would our substation maybe on the Fever. So, so we started saying, what are the things that could really go bad, and how would we better, build our system and develop an architecture that would anticipate. So some things, an earthquake, very hard to anticipate, right? And you're exactly right. Basically, our response now is we go out and look and see if anything's damaged. You know, you never know when one's gonna hit. So then we're out the next day looking at our pipelines, looking at our plant foundations, trying to see if any bolts have pulled up or any cracks in the concrete, any symptom that would indicate that maybe before we run this unit, we better make sure it's in alignment or take stock. So, But then a tsunami is a little bit different, right? You've got an hour or two of warning, you can make some decisions, and then like an avalanche, there's really no warning, but the effects of an avalanche, depending on where it hit, are kind of predictable. Like, we have avalanches every year that will come down and cross Power Creek and dam the water up, and all of a sudden the water will start drying up in the intake. So our analysis systems can know that and say, oop, we got a avalanche, it looks like, and we know that it's going to overshoot as soon as that snow dam breaks out. So let's maybe start a diesel and run that in the background for a couple hours until this avalanche thing works its way out. And we have those happen a lot. I mean not a lot, but 2 or 3 times a year we'll have some goofy thing like that comes very close to causing an outage. But over the years we've learned how to tweak our system so we don't have problems there. But, so I probably over-answered your question, but that's exactly what we're doing, is saying what are the threats and how can we just develop an architecture to improve our system, which is kind of hard because we have such a good system. So how do you improve a system that we already have 100% underground lines and whatnot? So one of the interesting concepts is tightly coupled and loosely coupled microgrids. So in a tightly coupled grid, electrically, because of the voltage and the frequency and the properties of electricity, and the fact that it moves at almost light speed, one device, sensitive device over here that's watching voltage and frequency can, at light speed basically tell if there's some kind of disturbance in another part of the system. So we use the electricity itself and everything connected to it to kind of keep track of what's going on. So your uninterruptible power supply that backs up your computer, if our frequency gets out of line, instead of 60 cycles a second, if it gets to 61 or 2 or 57 or 58, that thing might start beeping, because it knows immediately when it drops below that threshold. And so that's a tightly coupled grid where everything's actually electrically connected together. But then the concept behind a loosely coupled grid is that you kind of use communications to talk between different power plants, for example. So it turns out that we actually kind of run a loosely coupled grid at times. So our hydroelectric plant at Power Creek is talking to our diesel plant once a second all the time. And as long as those two are talking, the diesel plant knows that Power Creek is starting to spill water, and then it can turn off and pass all the control to Power Creek. So it'll do that. It does this all automatically now. Our operators only work 4 days a week, 4 10s a week, and our plants are unmanned at night and on weekends and everything. It's all highly, highly automated. We're at a state of technology that's ahead of even most of the national grid, and that's one of the reasons the Department of Energy wanted to work here. And so, so as long as there's communications, it's kind of a loosely coupled grid. But if we lose communications, Power Creek Road washes out, or that old corroded copper quits talking, which we've had a lot of problems recently while we're upgrading it, then Power Creek says, oh, I'm not talking with the diesel plant anymore. I don't know what's going on, and it doesn't know what's going on. So it says, okay, I'm just gonna go into a mode where I produce as much power as I can. And I can't see the rest of the system or town. I'm just gonna use whatever water is available and produce as much power as I can. And then on the other side, the diesel plant is no longer talking to that. So as far as it's concerned, it's just a electric load out there, like a negative load. It just sees, wow, I've only got a little bit of electric load out here, because out in the background, the power plant, hydro plant's taking all that. So that's more of a tightly coupled grid. So it goes from using communications to make decisions to just going back to the electrical parameters. So if the whole system speed starts to slow down, the diesel says, speed up a little bit, pull the fuel racks open. So it goes back to governing and controlling the system speed by itself. And so lose communications, Power Creek says, ooh, I'm not gonna try to control the system anymore. I'm just gonna start producing as much power as I can. The diesel plant says, ooh, I gotta be in charge now. I gotta control system frequency. So I'm gonna start a diesel if there isn't one started, and I'm gonna provide that frequency control and monitor it and make sure that I keep the lights on. So, and the idea is that ideally, this zonal approach, which is one of the 3 things they want to do here, is say you have a battery and a diesel in one part of your system, and you have a hydro with storage and a solar farm on another part of your system. Well, those can each be their own microgrid. If you have a battery and you have diesels, you have everything you need to kind of have a cost-effective power supply, relatively cost-effective, and let this grid run by itself. So if it turns out that this is all the upland, or say this is all the uplands in your community that are above the tsunami zone, and this is all the lowlands that are below the tsunami zone, if you see a tsunami coming, you can tell this grid, okay, you go into microgrid mode where you're taking care of your system speed and are self-sufficient, and let's open this switch here and let's turn this off. We don't want that diesel plant energized or running when a saltwater wave hits it. We want that to be just cold and quiet, and there won't be near as much damage. And meanwhile, we can run this grid, and then when things settle out and we can go back and start recovering, then we can look at picking this part of it back up. So that's the idea behind zonal grids. And there's ways that you can figure several grids. In the loosely coupled microgrids, this is a little more of a stretch, but say you have some villages out in western Alaska that are all fairly close to each other. if you have a big cloud front coming in that starts shading out solar panels and stuff here, they can communicate with other utilities and say, hey, you know, we got a storm front coming in, think about starting up a diesel or charging up your batteries or getting ready because you're about to lose some solar power. Or if you start getting a bunch of gusty winds and stuff here, it's like, hey, this windstorm's gonna make us shut our wind turbines down to protect them, so get ready to be without your wind turbines. So that's a loosely coupled grid. They aren't even electrically connected, but they can still kind of talk with each other and help predict disasters, so. Spent a bit of time there, but, so is there any kind of questions on how that works?
Yeah, I got one on the, you're getting a new battery this spring, right?
Yes, and I'll talk about storage, but yeah, go ahead.
Okay, I just wondered how big that's gonna be and where it's gonna be and what kind of protection you're gonna have around it.
Okay, great. We'll talk about that when we get to it there. And then this is just a more complicated figure, but it's not out of the realm of possibility even for our grid to look this complicated. So with the RADIANCE project, well, I'll just wait till I use that slide, I guess, and explain what we're doing. So this is the Cordova Grid, and really, it's simple architecturally. We got Humpback Creek out here. All the water in this basin drains and produces electricity. It's brought into town, comes to the diesel power plant by Shoreside, then into the town center, and then we have a transmission line that goes out here to Power Creek. So all of our power production is on that one big line there. And these are different power plants. Crater Lake may be a future part. For sure, a grid scale battery is gonna be a storage element. And I'll talk about those a little bit in storage. And then this just kind of shows how we broke down the responsibilities and what the different groups are doing. You can see it's fairly complicated. And then this is really the meat of what we were accomplishing in 2018. First, we had to define the resilience metrics, and this is a little deeper than you think because we say, what are all the critical buildings in your community? Which of those have backup diesel generation? And how critical are they? So like on a scale of 1 to 4, maybe a residence is a 4. Maybe that's not real important, or maybe a store, small business. Maybe pet projects isn't the most important thing to keep on during a disaster. Hospital, very high priority. Sewer system, water system, higher priority. Airport, pretty high priority. So we took all of the large power loads, 150 loads, and established different priorities for them. And then we looked at where they're located in the community, and then we looked at our electrical grid and said, how can we reconfigure to keep the most of those things on in different threat scenarios? So you end up with this big matrix, and you say, well, if an avalanche can take Power Creek out, but it's not gonna affect anything else, so let's not worry about that too much, but here's some things that we'll do if that happens. Where's a tsunami, big thing, or an earthquake? And then we want to build in the restore part of it. So the resilience metrics was one whole part of the project. Multiple networked microgrids. Really the part of this is what we call the system baseline model. And this is where the Alaska Center for Energy and Power came in. They have a lot of modeling tools. We've worked on a lot of projects with them before. And we have an amazing thing. Another thing that's really enticed the Department of Energy and the national labs is that when we automated our system 20 years ago, we put data historians in. So the 750 data points in our whole system, every single diesel piston temperature, every single hydraulic valve position on our hydros, every single hydraulic gate position, every indoor and outdoor temperature in our power plants, all of our bearing temperatures, all these power points, every single circuit, how much power is going on at different times, how much excess hydropower spills and when, how much diesel do we generate and when. And so this 18-year data set of 1 second data of all those data points that we saved is just modeling playground. And really, we might be the only hybrid microgrid in the country that has that kind of data set. So when you have all that data, and then you have a small disconnected system where if something goes bump over here, you can see the ripples over here, just as a great laboratory for them. So those things all are what helped lead us to this. So we built a system baseline model, which basically just says, let's take that data and see how does your system work, and if we make tweaks to it and stuff, how does it react? And then once they have that model, this year they're going to build what we call a digital blueprint. So down at Idaho National Laboratory, they're going to use some real devices. So they might take they might have an actual solar panel that they use to duplicate a solar panel in our system if we had one, for example. They might take one of the actual relays that we have and take our actual program out of it, our software program, and put it into the same relay and hook it up to the lab. And so they're going to build a working model of our whole electrical system there, so that they can build these zones in that digital blueprint and turn it on and off and see if it stays stable or if it works or not. And they can tweak it and add a battery here, add a solar farm there, add a small hydro storage here. They can tweak all those things and see how they'll interplay with the system. And as problems surface, they can tweak that model. And then the third year they'll come out and we'll install that in our system and see if we can, make this zonal approach. So that's the baseline model was last year, and we've completed that work, and now we're starting work on the digital blueprint. And then the third piece was a cyber secure architecture. So we went through every single one of our electronic devices in the system that can communicate, and we looked at what's the device, what's the firmware version, what's the software version, what's the actual program inside of it. We look at all of our switches and everything, and we start mapping that and building a cybersecurity plan on how to keep that system secure. And I'll talk about that a little bit as a separate piece. How long is this supposed to last?
You have all the time.
Okay.
that you
Am I
need.
wearing you out yet? Okay. Is there any questions so far? There's going to be more pictures and a little more excitement in the second half, I think.
If I leave quiet.
Okay, all right. So the field validation is what's going to work. So to be honest, working with a federal agency and the bureaucracy can sometimes move you backwards faster than moves you forwards. And that grant money that you get can actually move you backwards economically, because the project becomes the important thing instead of the outcomes. And for us, it's all about what's the value to you as customers? What's going to happen to your electric bill? What's going to happen to your the reliability of your electricity? Are we going to get off of fossil fuels or not? And so those are the questions that we ask ourselves. And so we built some structures into this that we have the authority. We get to pick the equipment that is or isn't added to our system. We can walk away from the project at any time. We have 3 specific spots where we take it to our board. We update them, say here's where we're at, here's what we've accomplished, here's what we've spent, here's the outcomes. Do we want to go on the next step, or is this not taking us where we want it to? So we wanted to have that authority, and it just helps keep the labs and our partners focused and on track, and same with us. So, and we also had to keep the existing architecture of the system intact. So we can switch to these grid controls, but if it starts causing mayhem, we can switch right back to the system that we run day in and day out that's very reliable for us. So we wanted to maintain control that way. So this was frankly, I cut and pasted a whole bunch of stuff together for this presentation because I had it available, but I gave a little presentation a couple weeks ago here on our cybersecurity plan, because the labs are telling us this is the state-of-the-art, state-of-the-industry framework. And it's fairly simple in concept, but again, nobody's really implemented it. So we'll basically come out of this with a mil-spec cyber-secure system, but it's going to be right-sized for a little utility like us to operate and maintain. And Craig's going to do all that in his spare time. So I always try to showcase Cordova first when I'm traveling, and just the scenic beauty and the amazing community we have, and of course the wild seafood. And so this is the team actually kind of implementing what's called it's kind of a zonal architecture for our system. So instead of having what you call a flat network where all these devices, every device can talk to every other device in the system, you have only devices talking to devices they need to talk to. And you can have groups of devices, and then a firewall to another group of devices, and then a firewall to another group of devices, so that if there's a virus or an intrusion into one part of your network, that can shut off and isolate itself, and your other parts can stay intact. And so for us, the logical architecture is Power Creek plant is a zone, Humpback Creek plant is a zone, our Orca plant is a zone. And we already have 2 servers in different plants that can completely operate the entire system, the entire control system. So the idea is that you don't lose the whole system, and then again, that you can restore the system. It's just like a physical threat. You know, you want to be able to anticipate a problem, withstand a problem, and then recover. And then there's a lot of things that you can do on those little connecting lines. You can monitor the traffic on those to see, are we getting way too much traffic here that we shouldn't be? Let's cut this off and take a look, or let's see what's going on there. So there's some diagnostic tools we can put in place as well. And then, so this is just kind of a reference, because cybersecurity can be very intimidating. Believe it, for us, it's very intimidating because everything's automated, right? So, and we don't build these devices or necessarily program them or dig into the guts of them. So, you know, if a bearing's broken, that's something we can deal with. If a network goes down, we don't have all the resources to go fix that whole network ourselves, necessarily. So, but it turns out, you know, 95% of the problems are not technical hacking into your system. Almost all the cyber intrusions are just physical attacks. Simple stuff like if you give away a bunch of thumb drives in an annual meeting, somebody will put a virus on one and set it outside your office door. So people coming to work in the morning pick it up and say, whose is that? First thing they do is plug it in to see what's on it, right? You're infected. Your own employee's just taking you right past your own firewall and plug the virus in. Or that janitor that just got the contract and is working for you and has access to your office, if you don't have your server locked at night and they can walk over and put a thumb drive in, you're compromised. And that's how most of the big hacks happen. Although there are some technical ones where you'll buy a device or a computer or something that has a backdoor built in that allows them to come in electronically and compromise your system. So just some simple tools. 2-factor authentication, whether it's a username and a password, or now you're seeing a lot of biometrics when you open your computer screen, it reads your face and then it starts up, and if anyone else tries to open it, it won't. So, and then we got credentials. So if somebody quits or is fired from the company, do you change all their passwords and eliminate all the access they had when they were an employee? Do you require more than one person to go into your server room and work on it, or do you have one of your staff go into a server if a contractor is working on it to make sure that they're not accessing it, you know, unsupervised? And then the physical access, just keeping your servers locked up. Control access, only give people the level of access they need. Not all 16 employees in the company need access to medical records, for instance. In fact, they can't, right? But all 16 employees don't need access to all the sensitive financials or to control the SCADA system. So that just leaves too many open doors and too much potential. So minimize the risk there. And then closing doors and windows, just like you do at your house. If you have a device that has 14 ports on it, instead of leaving all 14 of those ports active, just activate the one port that you're actually communicating on and shut the other 13 down so that nobody can come and plug a wire in and start communicating with it. So it's just kind of closing those holes. And then your passwords, change those periodically, and make sure that your vendors, we have a lot of highly technical and specialized equipment that they can, like our new battery, the manufacturer can remote into that and diagnose it, do all kinds of things. Well, do we trust them? Is the guy logging in doing it from his office there, or did he get fired last week and he's gonna wreak havoc on us to get even with his, you know, former employer? So we have those set up so that we can open them to let them in to do their work and then close them when they're done. And in fact, they'll automatically close if we forget. So those are just some simple, straightforward things that'll frankly take care of 80 or 90% of your problems. And then this is literally, correct me if I'm wrong, Stephen, but this is a new concept that really is front and center, and it's a cyber black start. If the worst does happen, and every single electronic network device in your system goes dark, how do you restore? How do you restore your network? So they call this a cyber black start. So for us, it's really changed our thought process because we have a diesel generator right now that is fully manually operable. I mean, we can pull the network cables, we can go down and start that thing. It has a manual governor, and frankly, we can keep our power on for the whole town in winter. You wouldn't even notice. And our whole network could just be on the ground on its knees. Now we're in the process of automating that and bringing it up to, and we still do kind of have it automated. We can start and stop it and do all these things through a controller, but if we disconnect that controller, it will still run by itself. So that's a great kind of legacy black start piece of equipment, right? That's old school. So now we're thinking some things like if we do build another hydro project, if we have a solar farm's a little harder because of the software involved, but hydro especially is easier to have all those manual controls built in at a very small cost. And it's actually a great training tool. So why not have that capability to run a hydro if you lose all network activity? So that's kind of changed our thinking a little bit as well. So what does all this mean? I mean, it's a lot of technology, it's all very exciting. These are fun projects, but it's a lot of time and money that could be spent elsewhere. So why invest our time and resources in grid modernization? So the board of directors' strategic plan is to have 90% of our electricity provided with renewable by 2025 and reduce diesel use to half of what we're currently using it by 2025. So we still use about 600,000 gallons of fuel a year, and we'd like to cut that in half. And frankly, we're doing a lot of things to reduce our fuel use. But the big pieces are gonna take some more investment and effort. So to get there, we're gonna have to do some things, and one of the things that's really missing on our grid is energy storage. Because there's times when we spill excess hydro, which doesn't cost us anything. The plant's already there. We can deliver any extra electricity from that plant at zero cost. The plant's already built, it's available. But then when we need energy at times and we don't have enough hydro, we have to run our diesel plant, and that's about 40 cents a kilowatt hour all in. Whereas our hydro costs about 6 cents a kilowatt hour for what we use it for. So that's kind of a valley of death where many times our system load, we don't have, well, now I'll have to get into a little bit about system stability and how an electric system actually operates and why storage is so important. And maybe you could have the lights back on for a minute, just so, because I'll kind of have to talk through this a little bit. So I've tried to use some human analogies to help explain this, but electricity is basically mechanical energy. So our whole electric system is electrically rotating 60 times a second, 60 cycles a second. That's what that 60 hertz is. And so it's just kind of like a car spinning along at a certain speed. If it's running along on flat ground, then you can have your accelerator at one spot and you can be going 55 miles an hour. Everything's great. But when you hit a hill, you start losing speed and your engine starts slowing down. You start bogging down because you put more load on that car. You're trying to ask it to do work and go uphill, but if you're not giving more fuel, it ain't gonna happen, right? So you have to speed up, you have to press your accelerator and pour more fuel to that thing to get it to speed back up and get back up to 55 miles an hour. Same with an electric system. If we're running along exactly 2 megawatts, all those big steel rotors are spinning along, and that's what's called rotational inertia. You can't put your finger on one of those things and stop it. It's gonna keep spinning, I guarantee. So the only thing that's gonna slow it down is to throw a bunch of electric load on it. So if the ferry comes in and closes the breaker to their shore tie and puts another 300 kilowatts on, your whole system tries to slow down. So somehow we have to very quickly pour more energy to it and speed it up. It's pretty easy with a diesel. The fuel rack just goes ring, and it goes ring, and picks it up, and then it settles back out. With a hydro, it's a lot harder, because you got this, Powder Creek is 8 feet diameter pipeline, 1.5 miles long. And so that water, I think I figured out weighs like 10,000 pounds a foot or something. That thing is a giant freight train moving down the hill at 10 feet per second, you are not gonna speed that up or slow it down. You'll burst your pipe in a heartbeat or flatten it like that if you try to, try to stop that water. So what we do is, I'm gonna cheat ahead a little bit, because this will help. Should put these slides in a better order. What we do is, this is called a spear valve here, and it's connected to the big water line's coming in right there, the big water line's coming in, it's coming up through this turbine. Inside of there is a big turbine like this, bunch of wheels on it, and through that pipe is a spear valve. And when that valve backs out, it lets more water go by to hit the rudder and make it spin. But that valve, you can open and close it, but it's not gonna change the amount of water going through because that's controlled by the water flowing down the pipe. So what we do is we have what we call deflectors. So that jet of water is going out and hitting the nozzle, and we have a sheet of steel that cuts part of that stream of water off and makes it splash off to the side. So it's just riding there, deflecting a bunch of water, and when the ferry comes in and hooks up, it goes ching, and instantly puts an extra 300 horsepower on. I mean, it's so fast and so responsive, it outruns the diesels. So we get super good power quality. So the good news is, we can run on 100% hydro. We don't have to have the diesels controlling our system speed. The hydro project's doing that. The bad news is, we're deflecting 500 kilowatts of power to do that. That's enough to run half of Trident Seafoods. It's enough to run the entire South Phil and the high school and that whole neighborhood behind it. So that's a lot of wasted renewable energy. And when we built the 6 megawatt plant and we only had 4 megawatts of load in the town, that was fine. But now we've got 8 megawatts of load. And all of Powell Creek plus all of Humpback Creek isn't enough to carry our loads at times. Even when we have enough water, we just can't get enough power out of the project. So we call that extra power that you keep in reserve to pick up loads spinning reserve. And a rule of thumb is 10% spinning reserve. So if you got 5 megawatts of load on your system, you want to have 500 kilowatts. So that's about what we carry in the summer. We've learned through trial and error that that's about how much you need if you don't want to have outages. You put too much load on and your system slows down and you can't pick the speed back up, we start opening circuits one at a time to take the load off. So that's why sometimes 13 Mile will open up. That's the first one to open up. And of course, that's the one all the board members live on. And so that one will open up to keep the rest of the system on. And then the system will quickly speed back up. That's the same as you got a dog sled team running along on the trail, and if they start to bog down, you kick a couple sandbags off and then they can keep going. You're just unloading the thing. So we do that as well. So anyway.
Do you use that analogy when you do presentations elsewhere?
It's amazing how many engineers don't understand this stuff. Seriously.
No, the dog sled.
Oh yeah. No, a dog sled is actually a super good analogy because, the electric system runs, it's called isochronous. Everything's spinning at the same speed. If you try to slow one generator down, you can snap the shaft on it because it is electrically and mechanically locked and spinning the same speed as everything else. Same with the dog sled. So you have one leader, and if the sled starts to pull down, he starts pulling faster, and that we have a unit like that. It's called isochronous. So when I was talking about Powell Creek being in lead, or the diesel plant being in lead, that's what I mean. There's one unit at Powell Creek that has a deflector going, but once we start the diesel, we let that be an isochronous because we want to pull those deflectors out and use all the hydro we can. Once we do have to use diesel, we say, well, we'll let you be the spinning reserve, and because we want to get all the hydro we can out of Powell Creek. So the dog sled's a really good analogy for explaining how each dog may run at a different speed, but that sled always moves. The system moves at the same speed. And if one dog gets sick and can't keep up, he gets drugged, right? He's going to go the same speed whether he's helping or not. And that's when you say a generator starts motoring. When it can't produce power anymore, like if you snap the shaft on one of those hydro plants out there, that generator is going to keep spinning because it doesn't have a choice. It becomes a motor at that point. So I kind of beat that to death, but that's kind of is how we back into what energy storage is all about, because there's different levels of storage. There's a really super fast twitch stuff, and that's what we call the frequency control. That's where you have to make changes in less than a second. In fact, we have devices that monitor the system speed in 3 cycles, like 1/20th of a second they can open up to protect life safety or to take part of the system off to keep it on. So These are really super fast devices. And so the analogy would be like glucose in your bloodstream. That's what keeps you on your feet. That is fuel that's already dissolved, it's ready there to burn, and it is literally in real time keeping you on your feet. And in our system, that's rotational inertia. So all those spinning devices and stuff, if you take all the water off your turbine, it's still gonna keep spinning because of the weight of the thing, and that's called rotational inertia. Well, it turns out that that takes a lot of the bumps and stuff out of your system. It will take the first shock because it's kind of slowing down at light speed before that deflector can move. So that kind of helps your system. So that's what we call frequency control or power class storage. And it responds in just a few milliseconds. And examples are like rotational inertia, flywheels, our deflectors, our diesel governors. Those are the things that are keeping the system stable. Short-term storage is a little longer. You can think of that as minutes or hours. And I kind of compare that to like carbohydrates. After you've eaten them, it takes you a little while, it takes you a few minutes to digest that and convert it to glucose, but you've got some pretty quick fuel available there, right? You knock back some toast before your cross-country match, you're gonna have some quick fuel. And that's kind of where batteries land. And micro turbines, compressed air, stored hydrogen, thermal storage, these things can store energy for minutes or hours. And that's where our grid scale battery lands. Then there's the real long-term storage, and this is energy class storage, where you're cost effectively storing kilowatt hours. This is a place where you can take all of a summer's excess energy and use it in the winter. And these are things like, compressed air can get kind of into the day's worth. Stored hydro can go for months. And then there's some other, frankly, diesel fuel and coal. What makes some of those energy forms attractive is that it's stored energy, and it's highly dense energy, and it's highly portable. So, you think about what you get in a gallon of diesel fuel for $2.30. It's really an amazing amount of energy in terms of horsepower. So it turns out we need all of those, right? We need a better way than wasting a bunch of hydro to control our system frequency. So we need something that's real quick and responsive, and that's our battery. And that's the main reason we're buying a battery, is because for us it looks like a free 500 kilowatt hydro, because that battery can take up all those fluctuations, and but it can also be charged and discharged. So while it's taking the place of the hydroelectric generator, say that we're just about to run out of hydropower and we're almost where we have to start a diesel. Well, that battery's charged up, it can discharge for a few hours. And it can deliver that extra energy before we start a diesel. Then when we start the diesel, we have to put several hundred kilowatts of load on it, and maybe there's not enough load on the system in excess of our hydro yet, but then we can have it recharge the battery. So that means that we aren't wasting, because right now what happens, right when we run out of hydro, we have to put it, we have less than 500 kilowatts of spare hydro. We put a diesel on, and we're wasting 500 kilowatts of hydro now. But then that diesel picks up another 400 or 500 kilowatts, because we have to run it at that minimum. So then that forces us to waste even more hydro. So now by using a battery, we can wait to start a diesel, and then when we do start it, we can use some of that to meet the system need, some to recharge the battery, and our wasted hydro is gonna go away. So that's the story behind the battery. And it turns out that it also has all kinds of grid resilience opportunities. So one of the ones that we're looking at is, this is just another sketch of the different classes. I was appointed to the the Department of Energy's Electricity Advisory Committee. So I sit on the Federal Advisory Committee, and it's amazing. I get access to just world-class technology. And my biggest takeaway from all that is what an amazing opportunity we have. We can do stuff here on our system that the National Grid could only think of because of all those regulatory barriers and everything I talked about. We can put one hydro turbine on and go to the Coast Guard and say, could you turn your breaker off and on a couple of times? And when they do that, we can measure how our system responds to that, and we can actually measure how much rotational inertia is in that hydro. Nobody knows. Turns out that's the big question. How much does hydro contribute to the rotational inertia on the national grid? We can actually measure that. So the Water Power and Technology Office is funding, half of that $6 million came from water power technology. And those are some of the questions they're interested in answering. So this was a chart they put together that shows in time steps, these are nanoseconds. This is how fast inverters on a solar panel can work. These are in milliseconds. This is synchrophasers and our protective relays. Those devices I talked about that can open on our system, they're down in this millisecond range. System stability, this is kind of in the hydro and diesel fuel rack range here in seconds there. And then wind and solar output is those kind of vary with cloud shading and changes in wind speeds and whatnot. Those are on the order of minutes. And then restoring a system is something that can take hours. And then the day ahead scheduling is what the national grid does. They try to forecast how much energy they're going to need based on the weather and sun and how much energy they're going to have available. And they put that all through this big, huge, giant supercomputer, and it says, well, we think your load's going to be such and such. And then that helps them decide who on the grid is going to be running their equipment and whatnot. It's highly complex. And then you get out here to years for system planning, because you got to make these huge investments and you don't want them to be obsolete in 5 years. So we got to look into crystal ball and guess where technology and equipment's going to go. And then you get out here to goals of like reducing carbon emissions and whatnot. And that's where you have to move the whole industry in a different direction. You're looking at maybe decades. So these are just an idea of the time scales. And these are all different kinds of software packages and platforms that do that stuff. So this is our battery. And to get back to some of Pete's questions, it's just an 8x20 container. It's literally a whole bunch of little batteries stacked together into stacks. Those stacks stack together into a module. Those modules stack together into a whole container. So this has the power output of 1 megawatt. So it can deliver 1 megawatt for about an hour. So it's 1 megawatt hour. So you can think of this, it could run all of Trident Seafoods south, or Trident Seafoods north in full swing for an hour. It could run the hospital, whose all-time high system peak was 150 kilowatts, for 8 or 12 hours. So that kind of gives you an idea of the storage here. And meanwhile, though, it's controlling system frequency, so we don't have to have 400 or 500 kilowatts of room on a diesel anymore. If that's a 2 megawatt diesel, we can run it right up to 1.9 megawatts because the battery's in the background. And if we get a big, huge load all of a sudden, it's okay, the battery will pick it up. It'll give time for the other diesel to start, or even just wait a while. Let's not run into starting another diesel, maybe the loads will go back down. So that is gonna take, we think it's gonna cut the starts and stops in half on our diesel fleet. And we have an aging diesel fleet, and believe me, we do not wanna make any investments in that diesel fleet, we don't have to. We'd rather move in the other direction. So this is gonna take a tremendous amount of wear and tear. And then it starts getting into other questions like, what happens if you take a diesel fuel rack and tighten it down with a wrench and lock it at exactly 1 speed and let it run there and let the battery take up? What is the fuel efficiency of that diesel? Nobody knows. There's too much noise on the national grid to measure things like that. But if on our grid, we can lock that thing down and we can run it for 24 hours, say at 1 megawatt, and then we can put it in ISOC until it averages a megawatt. You just fluctuate the loads so that it averages a megawatt, and then see what's the difference in fuel, and we can answer that question. So,
I got a question.
you betcha.
So this is a metal Connex container, right?
Yes.
So is this almost essentially EMP protected?
So electromagnetic pulses. What's really susceptible? I'm going to say yes and no. So because it's completely surrounded by metal and it's going to be highly, highly grounded. One of the kind of the side things we're doing is for life safety and for the protection of our equipment and everything, we're expanding the ground grid at our substation. This is going to go down by EAC plant on Lefevre. So we're going to have it tied to ground grid. So yes, lightning could strike this and would probably be okay. However, there's electronics are what's really susceptible to electromagnetic pulse. We're probably as protected as any system in the country from EMP because our underground power lines, and they're shielded, everyone has a neutral around it. So, but what isn't protected is our electronics. And this gets back to the cyber black start thing.
Right,
So-
well, you've got the option of manually running the
Exactly.
diesel generator.
Yeah.
so.
So that diesel is, and that's very, very unusual. I bet there are not many legacy plants that can run in full manual mode now, so. That's a good question.
What's the expected life of that battery?
That's a good question. In fact, it's $1 million question. I'll answer that, but here's what the project cost looked like. It's basically $2 million all in. We're getting assistance from the Department of Energy. In fact, we got another $335,000 piece from PNNL, Pacific Northwest National Lab. And so I'm trying to keep our total cost around the $1 million range with that additional from Pacific Northwest National Labs. We might get there. So battery life, lithium ions batteries are interesting because if you charge a grid scale battery up or a lithium ion battery up and you completely discharge all the electricity out of it, you only get to do that 5,000 times. Now that sounds like a lot, but if you do that twice a day, that's 700 times a year, you get about 12 years out of it. $2 million is a lot of investment for that kind of life. And then, so if you do the math, you say, well, 5,000 times 1 megawatt hour is 5,000 megawatt hours, or what we call gigawatt hours. So that's about what Humpback Creek produces in 2 years. So that's how much you can charge and discharge at. You get about 5 gigawatt hours out of it. Now it turns out, if the shallower and shallower you do those discharges, the more times you can do it. So I'll give you a real example, is the best way to explain it. Say the battery is taking care of our system frequency, and we have the hydro running behind it, we're 100% hydro, we got the battery, and Triton Seafood starts a 500 kilowatt compressor. And say that it takes a minute for our hydro valves to open up and slowly pick up that extra power. Well, that battery is gonna provide let's say 480 kilowatt hour, or 480 kilowatts for a full minute. Well, a minute is 1/60th of an hour. So if you divide 480 kilowatts by 60 minutes, you end up with 8 kilowatts. So it turns out that's an 8 kilowatt hour energy hit on it. So even though it's 500 kilowatts, it only lasts a minute. So it ends up being 8 kilowatt hours. Well, 8 out of 1,000 is less than 1%. It's just less than 1%. So it turns out that once you drop below that 5% depth of discharge, which I think will stay out of that land all the time for system frequency, you can get tens of millions of cycles. That's what the manufacturers are telling us. So it turns out that if you multiply 10 million times, like, say, 10 kilowatt hours, or let's go 5%, so you got 50 kilowatt hours, and you do that times 10 million, now you're up to 500 gigawatt hours. So your 5 gigawatt hours or 10 gigawatt hours you started with, because your shallowness cycle is now 500 gigawatt hours. It could last 30 years. And then, now I wish I brought the summary slide on batteries. So, but you don't wanna just, we're not gonna have it for 200 years, right? So if we're also doing the big charges and discharges, like I already explained, that's also gonna save us fuel, right? We don't wanna leave that off the table. So we're gonna do both. Well, it turns out that there's only certain times, sometimes a year, we're gonna have to run a diesel no matter what. So, we may not be discharging and charging much. Over half the time, we're over 100% hydro. So it turns out there might only be 100 or 200 days a year where we have to charge and discharge that battery. So we're hoping to get 30 years life out of it, is to jump to the answer. And that's one of the things that the Department of Energy is investing in. Nobody knows how long they last, but nobody's measuring each discharge and how deep the discharge and keeping track of that over time. And that's one of the things that funding is gonna do. It's basically gonna pay us to collect that data and provide it back to the department and teach them things about lithium ion batteries, so. But the way that they, when you say they wear out over life, or over time, you'll always have that one, actually it can provide 2 megawatts of power for a half hour. So it's incredibly powerful, but that doesn't change over time. What happens is that it's about a megawatt hour, it's actually 970 kilowatt hours. That's what you lose over time. You have less and less and less storage over time. But remember, we only need 8 kilowatt hours to handle our big biggest load, right? So what if that thing degrades really rapidly and after 30 years we only have 100 kilowatt hours left? We can still use it for the most valuable thing, which is replacing the hydros for frequency control. So I'm fairly confident we'll get good life out of it. And then I think you were starting to wonder into safety around it, because one of the big failures with lithium ions is fire. So one of the things that the Department of Energy is paying us for, and that we'll be working with emergency management, is having an emergency response plan. So one thing is siting it so that it's not in an area where it's can hurt anything if it does catch on fire. Then there's special ways that you have to tackle a metal fire like that. So we don't expect that to happen, but we want to have a plan in place in case it does. And then of course we have warranties and stuff to protect against that. So we're kind of at question and answer time. I'm gonna see if so Crater Lake, I'm gonna do another presentation in 2 or 3 weeks. This is just another storage element. So it's a large scale storage that can store water from one season to the next. And that's it.
So what's the power output from Crater Lake once it's established?
You know, it really depends. There's only so many kilowatt hours there. So like the battery, there's a lot of ways that you can manage a megawatt a megawatt hour of storage. You can deliver 4 megawatts for 15 minutes, or you can deliver just a tenth of a megawatt, 100 kilowatt for 10 hours. Same with Crater Lake. So, you know, I originally thought, I mean, the economics says a smaller generator, like 500 or 600 kilowatts, and then because you're delivering water to the community water supply while you're producing that. So if you try to produce 2 or 3 megawatts, you're gonna be ripping through that water much faster than the city can use it. So you're wasting water at the gain of electricity. But the city can't use all that water. There may be other ways to pump water into that system, we call pump storage. That may make more water available, and maybe that water is available for sale. So maybe you wanna have a bigger generator there so that if you fill a water barge or something, you can generate more power. So these are some of the things we think about as we think about how would you finance that, how would it pay for itself, what's the best value to the community.
In terms of size, how does Crater Lake compare to the battery?
So
If you look at Crater Lake like it's a storage battery.
okay, so a battery in one cycle is 1 megawatt hour. So in a year, on average, Crater Lake would be like 2,000 megawatt hours. So it's about 2,000 times the storage. But then you can recharge the battery many times. You can only recharge the battery once, Crater Lake once a year. So not a completely fair comparison, but that's why hydro storage, some storage options are very good for storing energy, and they're good energy class storage, but others are really good for power. It's like if you try to control system frequency with Crater Lake, I mean, you're talking about something that even for Power Creek cost us maybe 500,000 kilowatt hours a year. Building a 2,000 kilowatt hour a year project to do the frequency response wouldn't work, but the energy is valuable. So, yes.
Would the co-op own the battery?
We do. We own the battery.
So are there other batteries, have they produced other batteries?
Yes. So
And
this
are
is.
they in service now?
That's a very good question, and I appreciate the question behind the question. So we are willing, if the value proposition is good enough, and if we have good partners, to be on the leading edge of technology, but we don't want to be on the bleeding edge. So one of the reasons we chose SAFT and ABB is they're very large, very financially capable firms. They both have battery packages in Alaska. This package, almost identical to ours, is in Kotzebue and has been there for a couple of years. They've got a package in Chugach Electric. Well, they've got the ABB package and then a different battery. And then I think there's a SAFT ABB package out in Kodiak maybe. So, and then worldwide there are quite a few of these. So it's pretty commercial grade technology. So yeah, there are others in service. So we're
Have you pursued the idea of just leasing the battery from these people instead of purchasing it? And they're being on the front edge of newer technology coming in. You say your battery's gonna last 30 years, but
Yeah.
you would expect that there would be new technology during that period of time. It seems that it would behoove the co-op to keep their options open to continually upgrade the system.
Mhm. So, and that's one of the problems with new technologies is you invest in one and, you know, like computers. You buy one and 2 years later, there's one that's twice as fast and twice as good and cost half as much. So that is a point of entry is kind of hard, and then the risks of new technology. And we just kind of balled that up and said, well, right now, with the picture of our system, if we have this battery for 10 years and it becomes obsolete after that, we're kind of at a break even at that point. And a big part of our investment is having a warranty and factory maintenance on it, so that if we have a guarantee that if it doesn't last that long, if it doesn't produce what it's supposed to produce, if it doesn't function like it's supposed to, then they're on the hook for it. And so, and the battery modules it's all modular, so those batteries can be replaced. The whole package can be lifted up and relocated, repurposed. In fact, the cells themselves can be repurposed for things. But I think we're gonna find that we really don't need to replace those cells, that we can just let them keep degrading. And as long as we're using them for frequency control, we're fine. But you can change the modules out one at a time as the chemistry improves. What I hear in a lot of the presentations from the labs and whatnot, that there are not big gains left to be made in battery chemistries and battery structure. They don't think that there's gonna be some whiz-bang breakthrough that gives you a battery that stores twice as much or lasts the lifetime is something that they're improving all the time. So, in fact, this chemistry we have is something that's just been out for a couple of years. They've added aluminum to their cadmium, lithium, nickel mix. So it's supposed to lose 0.5% of capacity a year to what they call calendar aging instead of 1.5. So if you never cycled your battery at all, you're still gonna lose 1.5% capacity a year. Well, in 10 years, that's 15% a year capacity. And ours, they've modeled and tested, and they're saying it will only lose 1/2. So we're gonna measure, so we'll find out.
Thank you.
But yeah, we look at leasing and stuff, but the problem with, one of our problems, it's, if you can just bring it in on a rail car and set it down and then leave, then it's great, but so much of the cost is in the work we have to do at the substation and the shipping and back, that, and a lot of times those leases are tied to your savings. So if we're charging it with 6-cent power and offsetting 40-cent diesel, if a vendor's gonna have some risk and some ownership, then they're gonna want a piece of that savings. So some of those lease arrangements give them the savings. We are willing, after a lot of our research and because we have partnership with the Department of Energy, we'd rather the members had those savings and get the benefits of the batteries. Yeah,
How's our hydro doing right now with the nice weather?
it's doing terrible. So it's, you know, this speaks to solar, and we are looking very aggressively at solar. The cost has come down so much, and the performance has come up so much, and it's actually a very good complement with with our run-of-the-river hydros, because this is what happens. We get these cold spells and we get this high-pressure cells, and if we had solar panels out at the airport right now catching that reflection off the snow, our best solar penetration of the year is in March and April, and that's exactly when our hydros perform the worst. By then, the mountains have drained out, we get that sunny weather, so solar's becoming a better and better option for us. And then what really the middle piece, and it's why the battery's very helpful, because if we have a 1 megawatt, or even if we have a 200 kilowatt solar farm, and we can use the battery to charge that up, and then, you know, be flexible when we use it, those work well together. It's where a stored hydro or a pumped hydro can really help too, because then if you have a megawatt available, or say we size it at 2 megawatts, if you have 2 megawatts of hydro available, when you don't have solar, then you can kind of trade those off against each other. Use the solar when you have it, use your stored hydro when you don't. So do you know what our numbers of hydro, what our hydro percentage is right now, Scott?
Right now, it's probably about 15%,
So we're 15% hydro right now.
or 400 kilowatts.
So 400 kilowatts, they're using 2 megawatts of diesel right now. And there were times in January where we're spilling hydro all over the place, so that's the frustration.
Is a part of the system too to have like smart meters at our house?
Yes,
So there can
thank
be
you.
differential pricing?
Thank you. So I haven't gotten into the grid technologies and where we're going with all this and what's the value to the members. So great, you know, you do all this architecture and zonal configuration stuff, what's that gonna do to your rates? And the lights stay on most of the time anyway, so why are we trying to improve that? So the battery answers part of that question, but then there's where we wanna take the battery. So if we have a system-wide blackout, we've got that battery sitting there with a megawatt hour of stored energy available. 3 blocks away is our community hospital. That's one of the reasons we sited it where we did. So if we put some new controllable switches in place of our oil switches there, we can tell those things, okay, configure the battery to be grid forming so that it can control system frequency and deliver energy by itself, and then close it into the system, just part of the system, close one feeder to that switch, close the next switch to the hospital, and energize the hospital, and we can run the hospital for 6 or 8 hours. So you say, well, that's nice, so how does that help? Well, right now, the hospital is under, their diesel plant is so aged, they're looking at having to upgrade their diesel generators to provide emergency backup. There's federal regulations that require that. And frankly, their system's pretty old and it's not working real well. So they're getting quotes of like $500,000 to $600,000 to upgrade their diesel plant. That's very frustrating because that's a system they're hardly ever gonna use. By the time they do need it for any amount of time, there's probably gonna be water in the fuel, or the start batteries will be dead. Just from my own experience, I know that they're not in the energy business, we don't expect them to be. And so that's a huge colossal waste of resources. So if we've got this battery that we can use to do spinning reserve and arbitrage, you know, charge it with low-cost hydro and then keep our diesels from starting, our high-cost diesels from starting, and then we can also use it for an uninterruptible power supply for our hospital, that's just saved several $100,000 of investment that would be a waste for the community. So that's an actual part of this project, and there's actually a budget from the federal side of Radiance to buy those 3 switches to automate that. And again, this is something, people are talking about doing this, nobody's actually done it. Nobody's made a grid smart enough that if you've got a battery that's sitting there doing all this stuff all the time, that in an emergency it can do this whole extra thing over here. And so that's, and then it gives us a whole opportunity with meters, because now with I'll call them smart meters throughout the whole system, we can tell when to turn off and when on. We can control when we turn certain meters off and on, right? So say that we only have Humpback Creek available. An avalanche hits Power Creek, the diesel plant catches on fire, all we have left is 200 kilowatts at Humpback Creek. We can turn all the meters except the hospital and the water plant off. Maybe there's 2 homes in town where people have respirators and emergency medical devices, maybe we leave those on. And maybe we turn the airport on for 3 hours for flight 61 and 3 hours for flight 60. We can control all that through dispatchable meters. And more importantly, in one of the assignments that the Department of Energy gave us is they want us to dispatch excess hydro to an electric vehicle. So we're gonna work with partners and whatnot to work and to try to use an advanced metering infrastructure, because our system's smart enough. It knows when we're getting close to having to start a diesel or getting close to spilling hydro. And it can say, wait a second, help us out for a minute, battery, while we start charging electric vehicles. And so now we start really, really making hay, because now we have places to give you that electricity, and we can use time of use rates. So we say, hey, if you'll wait to charge your car, or the last 25% of your car until we have extra hydro available, and instead of spilling it, maybe we can sell it to you for 5 cents instead of 20. And now, instead of being half the price of gasoline, it's 1/10 the price. that's when we start, really making hay. And, same with the diesel. If everybody's using electricity and we say, wait a second, my refrigerator doesn't have to cycle every time it gets down to 32 degrees. Maybe I only let it get down to 34 degrees when our diesels are running, and maybe the refrigerators are only cycling a little bit around town, and it keeps the loads low enough that the diesels aren't starting. So that's what a smart grid starts looking like. And then things like, say, it's not cost effective for the city to install a meter on every single water service and go read every single one, right? But then, and then this is gonna kind of actually end up being an argument against Crater Lake. So if you have if you have a water valve, install a water valve that can measure the water that's going to your house, but it also has an electric solenoid that you can open and close it, and it communicates. In other words, it's kind of a smart device. Maybe it costs $200 to install that meter, but now, if you're only paying for the water you use, so what's gonna happen to the use patterns? If you're gonna pay for what you use, you're gonna be more careful with it, right? So as we put more and more pressure on our water system and start looking at having to make multi-million-dollar upgrades to grow the capacity, if we have smart devices that help us use it more efficiently, maybe we don't have to make that big investment. So now those little water meters through the system could be saving millions of dollars in infrastructure investment. But then, if you're on vacation and you get a steady flow through your meter, you can get a text that says, hey, it looks like one of your toilets is hung, or something's using, you got a leaky faucet, would you like us to close the valve, send a plumber, do both? And you can do it from your smartphone in Tahiti. Or, God forbid, there's a real fast water flow, hey, it looks like you got a broken water line, do you want us to close that valve or send a plumber or whatever? So now we're starting to provide better service and options to you at very low cost, and those smart devices can communicate through our meter or through fiber to the home. And this is a great thing about two co-ops, we can work together to say, let's not both make the same investment here, let's, why don't you do fiber here, we'll do, a smart meter there, you can do an Internet of Things device there, and private sector can do this, and then we start getting a real efficient system that takes us to a different place. Then you could take that same valve and put it on your fuel tank. Now not only can you tell how much fuel you're using and stuff, but it can let you know with the text whether someone's stealing fuel, or God forbid you got a fuel leak right next to the river or the salt water, and you can close that valve remotely. And even healthcare. I use an example of, now instead of having to be in a hospital, maybe you can be at home with a monitoring, they've already got that X prize for the iPhone that can out-diagnose the 10 best doctors in the world. So if you have just a personal monitor and a Wi-Fi connection, if you start to go into cardiac arrest, maybe a mini drone comes out and lands and gives you a shot of nitro. And, or your doctor 5 miles away or 5,000 miles away can say, hey, it looks like you're maybe not doing so good here, would you like us to send an ambulance? Or wait a second, your potassium's getting low, but increase your drip rate here a little bit or whatever. So it just opens up a whole new world of possibilities. And so we've been building the platform to do that. So those smart meters know when and where there's an outage. So when we have 100 homes out of power now, it can automatically populate. We've already got technology in place that can connect the accounts to the meters that are out to our mapping system and post a map on the internet, so you can just go to the outage page and see, oh, those parts of town are out. And maybe we can push a text out just to anybody who's out of power and say, hey, looks like somebody dug into our power line. We think we'll have it on in about 2 or 3 hours, but we'll keep you updated. And so again, we're getting a lot of value through some incremental energy savings and stuff, but now it puts us in a position to provide a lot better customer service and choices. And